Okay, so this computer is a bit slow, so because of that, you may have some interruptions. Now, can you guys see this in whole screen? Just talk it, right? So I am not reading your chats because I am looking at the full screen video, full screen presentation, right? So if you have any questions, just unmute and ask the questions. Okay. Can you guys see the full screen?
Yes, sir.
Can someone yes, right?
Yes, sir. We can see.
Okay, great. Thank you. So we will start our today's lesson. Today's lesson is feature engineering and optimization. Okay. So actually what we have done up to now is about changing some topics one by one, like algorithm a certain week, and then we come to another theory part and so on, right? So actually we are moving in that way, right? So after the support vector machines we did in last week, you guys may find that it may be a bit confusing because we haven't proved everything. We just mentioned the uh, uh, outcomes of these theories, right? So we didn't tell how each of the theories coming and what are the rationale sometimes behind each of them, right? So that's why you may have find some difficulties, but don't worry, because we are not going to ask any difficult questions from those uh, lessons, because it's open book. So I will not make it difficult in the MCQ. So by the way, can you guys? I think you guys have seen in Moodle, right? So I have said that I'm not sure the exact day of uh, the group assignment. So we have to submit it, right? I think 3 weeks after the around 3 weeks after the day I have published it, right? So there's a group assignment for member groups. So you have to do some it's an open-ended question, right? So you have to do some machine learning task end to end and submit it. So everything is given in this documentation, right? So and also at the same day the submission, in that particular week we will have the uh, final in-class quiz, right? So that would be covering the later parts of the lessons that we have covered after the first in-class quiz, right? So that will be in the same way like we did it earlier, right? So don't worry. So I try to make it bit easier this time. But anyway, just study well, because you will not be able to just search in the lecture slides and find the answers directly. So just if you just have to understand it. Right? So don't worry about the mathematical equations, how they come and so on, how they are derived and so on. Just say that uh, so what we want is to know how the machine learning and its theories are interconnected with each other. Why we are selecting a certain algorithm? What are the things that we have to do when we see a problem? Right? So, like as you are not going to be mainly data scientists, so you are not going to create machine learning algorithms. What we have to do is that to learn how to apply the existing algorithms that are already built with like libraries like scikit-learn and other such Python software, right? Python libraries. We all these uh, theories that we have given, all these machine learning algorithms are available, right? So you just have to use them. But I am so you may think that. Actually, most of the people think that why don't we just tell you how to write code with Python, right? So actually, that is easier, right? Because some of these codes are given as examples in our tutorials, but before you apply it, so you should know what are the things that you should do with it. Like there are many parameters that you have to train, and there are different ways that you can use these algorithms, right? So although you can just simply use the algorithm, doesn't mean that you can simply uh, apply it for whatever the problem at your hand, right? So depending on the problem and depending on the data and all the circumstances, uh, you have to select what you have to decide what you should do with the programming part. So that's what we expect from doing all these theories, right? So not about not to prove any theories or something with a partial differentiation or anything like that. So just you just have some understanding uh, why we do it and what is the rationale behind selecting selecting a particular algorithm, and what are the things that you can do if that a data set is in a certain way and so on, right? So that is the idea why we are doing all those things. So actually we may be running out of time, but it's important, I thought, discussing all those things before we start the today's lesson, right? So and if you actually I thought that today's lesson was a kind was on in the class, because today morning actually I got to know that this is going to be online. So anyway, so I will try to use wait a minute. I will try to use yeah, we can use the uh, pen if we want, right? So yeah, then no worry. Right, so today's lesson is not, again, because the last week we were doing algorithm, so today we are moving back into our theories, not mainly the theories, but the basics of some data science, right? So although this is our subject module is known as statistical and machine learning, uh, we should if we study only these statistical parts and statistical theories and machine learning algorithms, there may be some missing part that you will have, which are related to data science, right? Basic data science means mainly that is covered in earlier. It was covered in this our exploratory data analytics, right? So it's not a theory, but it is something that you get familiar with, right? So when you have a data set, we can't say these are the steps that you have to follow to to do the exploratory data analytics, right? So, so other than looking at this like the shape, the size, and all those things are common, right? Other than those basic explorations, we can't exactly say that what you should do as a process, right? When you find there are some missing values, I mean there are some uh, error values, there are some outliers, when there are missing like incorrect data types and so all those things. So when you see all those things, then you have to uh, do the EDA, exploratory data analytics, and you have to remove them, update them, and do all those operations, right? Actually we can't uh, teach each and every uh, operation that you have to do, right? So actually it's a self-learning process, because self-learning is that when you actually when someone is passing out from graduating from a university, they don't know exactly how to deal with each and every data set, right? So that comes with the experience. That's why I say that if you have time, and if you have some passion in moving with this subject, so you have to do some Kaggle exercises and do your own learning with the course that I have given. you can do it. And there are some online tutorials if you want to master some of the Python libraries like Pandas and NumPy, right? So do those things yourself, because subject is very, I mean, it's large, right? So it's because of that we can't exactly say this is what you should learn, because there are a lot of things that we actually teach only 1% of machine learning. In the, if I say honestly, right? So when you go to the industry or when you are facing some problems, you will find different ways that you can do it. Because of that, you have to make your hands dirty with working stuff. So actually, I'm wasting some time, but I think it is important. Before we start the today's lesson, because this is also a very practical lesson, although it is a theory. This is about learning how to do the data science. Like it's like the second lesson of our data science. The first part is about exploratory data analytics. This is like the second lesson of our data science series. So this is mainly about feature engineering and optimization, right? So what is a feature? So you know it, right? So no need to tell, right? So features are basically the independent variables, right? Independent variables or X variables or predictors in the terms of statistical machine learning. Right? So actually, feature is a way of defining the input information for a machine learning algorithm, right? For a machine learning training model. So features are the X variables, right? So it can be either numerical, it can take numerical values, like, you know, numbers like integers and float values, and categorical labels, like there are like genders, months, uh, colors, and all those things, right? The categorical variables, you know, there are two types of categorical variables: nominal variables and ordinal variables, right? Uh, in the numerical also there are two types, right? Can you remember? Numerical, there are two types. What are those two types? Continuous and discrete, right? So continuous means something like a float data types. So the number is continuous, like temperature, height, and all those things. And there are discrete means the numbers that has discrete values, like number of people, uh, and so on, right? Which is represented by integer values, right? And the categorical labels, there are two types: nominal categorical variables and ordinal categorical variables, right? Like nominal means it has only a type, so like color and so on. There's no order between each of the colors. Like actually, there's no relationship between colors, right? When it comes to gender, also there's no like this is the smaller gender, this is the larger gender, and so on. Color also, there's nothing like a smaller color, larger color, and so on, right? Although there's a frequency spectrum for colors, but when it comes to colors, we generally take it as nominal categories, right? And in the and they are in when it comes to the ordinal types are like age groups, t-shirt size, and so on. Age, so all those things are also categories like age groups, but when it comes to age group, there are like smaller age group, like age lesser than 5, and age from 5 to 10, and age 10 to 30, and so on. So there is an order, although they are categories. So those are known as ordinal data types, right? So there are two types for categorical data types: nominal types and ordinal types, right? And there can be, and features can be complex data types like images, videos, and texts, right? Actually, we are not going to discuss about the third type in this module. So mainly maybe we can actually if you want to do some classification with some text and or images, you can use the algorithms that we have learned. But because this is more only a MBA, we are not going to discuss much about this kind of examples. Because what you have to do is you have to deal with structured data. Can you remember what is structured data? Structured data is tabular data, right? Mainly, like that can be represented in a table, right? So, wait a minute. Can you remember the types of data? Like structured data means that so sorry, sorry. I am not familiar with writing all those things in. So we can add the data in tables. So this is very ugly. Don't worry. So those are the data that is represented in tabular structures. So which has these column names and these rows, right? These are known as structured data. So we are going to learn mainly about structured data, not about images and audios, videos, and so on. Right? And when it comes to features, the idea of doing feature engineering is to find high quality and independent features. Right? What is high quality? High quality means the information. So the idea of having features is getting some useful information into our machine learning process, right? So that means you can add some non-related uh, uh, information. For example, if you are talking about the economy of a country, you can take uh, uh, some data related to another country or something like that, right? Which is not related, and there can be data that are not related. So the idea of quality is that the data should be related, and data should have the information related to that particular uh, thing that we are going to predict. Right? For example, if you are going to find uh, find a diagnose a particular disease, uh, the features should be relevant to its the patient's symptoms, right? So that is what's about high quality information. So those features should bring most information into our machine learning model, and they should be independent. Independent means we should not have two or more features that are giving the similar kind of information, right? For example, if you want to evaluate the land, uh, evaluate to predict the price of a land, you can take the distance from the main road, distance from the railway, from the railway station, distance from the hospital, and all those things. So all of these may be related to are correlated, right? So instead of that, having the distance from the main road may be sufficient, right? Because most of the so maybe this example may not be a better one, right? So you can just think, right? So you should have independent. That means the information should not be shared with each other, and they should have a higher quality. And that means when you are having independent means when you do a pair plot, right? So as we discussed in EDA, you should have independent data. Practically, you may not get independent data. You may get better to have highly unrelated data when you are having these pair plots or the scatter plots between two, right? So it should be like when you are independent, your scatter plot should be having random values like this between two x values. So that means these two variables are independent. Right? That is how you find the correlation. Right? And so although you can have too many features that can improve the model, that doesn't mean that you should add too much features into your machine learning model, because too much features means it is difficult for the machine learning model to learn or the extracting information when the noise ratio is higher than the real information, right? So that means when you are having, so if you learn about information theory, you will learn that there's a thing called noise. Noise means unnecessary information, unrelated noise information. So when you are having too much correlated features or non-related features, you will have too much noise into, you will introduce too much noise into your machine learning process. So that would difficult for the machine learning model to come to a solution, and also it would increase the computational burden to your computer, because if you can do it with 3 features, if you add 30 features to do the same thing, it would take much time, and it would take memory, it would take a lot of computational CPU cores to CPU or GPU cores to process it. And although you can process it, even though you process it, still you may get lesser accuracy, because most of the information that are given by unwanted features are noise. So when the model is going to fit to the noise, that means the model will get less accurate. Because of that, we have to find features, right? So here, selecting the correct features is the most important thing in a for a machine learning, for creating machine learning models, right? So you learn all these machine learning algorithms from these lessons, but when it comes to practice, how you as an analyst or data scientist differentiates from another one sorry, from another data analyst or data scientist, is how you do these pre-processing stuff, right? Pre-processing means what are the features you select, how you remove the noise, how do you filter out unnecessary information and create features that are very relevant, right? So you may get a set of features, you may get the data set, but these data fields may not be related to the information that you want. You may have to generate some features out of it. So only then you will get the highly accurate model. The machine learning models are there, they are built with Python, but when it comes to creating a model and having a highly accurate model, you have to have some domain knowledge, and you have to have the machine learning knowledge to extract this information, the most important features, the selecting the important features and remove the unwanted features to have a better model. So we have actually discussed this earlier, right? So you can add the number of features, right? Like this. So adding number of features means you are increasing the model's complexity, right? Complexity means the model will have too many parameters. But when you are adding too many parameters or the number of features, actually parameters are features are different, right? So parameters are some the the machine learning model, the number of inside variables are known as parameters, right? Features are the input parameters, right? So that is the difference, right? So when you say parameters in a model, that means the number of variables that we trying to predict. So the values that we are going to get for a model, so that is known as the parameters, right? So if this is the model, so we have different variables. So these are known as parameters. We have some input data fields, right? Those are the features, right? So now when you increase the number of features, you have to definitely increase the number of inside parameters, right? So then the model will get complex. So when the model will get complex, what happens is if you measure the error level in the model itself, you will see that the error level is decreasing, right? Error level means we are comparing it with the data set that we have used with training. So it is going to be reduced continuously, but that doesn't mean that the model is working better, giving better predictions for unseen data, right? What are the unseen data? So the training data is the data that are seen by the machine learning model. So that the data that haven't been seen by the machine learning model are the test data. So when you increase the complexity, after a certain point, you will see that the test error is increasing, right? That means after a certain point, the model is overfitting, right? So we have discussed it earlier. So when you, after this point, the overfitting effect is higher, so you have to stop at this particular level of complexity. So this is the ideal solution. So that means you have to select the features that are giving this amount of complexity. Find these features and creating better features are what we are going to learn in this lesson. So when you are adding new features, that means you can actually change the features like we discussed earlier. Like we can take the polynomials of, if we have features x1 and x2, we can take the polynomials of x1 and x2 and add it as the features to the model, right? Then we can test how the test set performance is affected, and then we can decide what are the features that you have to use, right? So what you have to learn is, remember, is that adding new features may increase the model accuracy, but that is only for the training set. What we want is to minimize the error in the test set. So that is how we measure. That is what decides where you should stop adding or removing features, right? And then the process is, this is how we do the feature selection. We have to minimize the test errors, which is known as test feature selection, right? So now say that you have n number of candidate features, right? Now, how many ways that you can select r number of features out of this n number of candidate features? There are this much of ways that you can select it. If we are trying to validate to find the test errors, you have to run it this much of times to find the errors, and you have to find the minimum one, right? And actually you may not know the number of features that you want to have in your model, right? So there are n number of candidate features. You don't know how many for what, which are the test error will get minimized. So you would have to run test r for all the values, right? So then you would have to try this number of examples, this number of not example, sorry, this number of tests. You have to run this number of tests to find the test accuracy, find which one is the least one, right? So this is very inefficient. That means when the n grows, this term grows exponentially. That means when the number of candidate features are increasing, the number of tests that you have to do increases according to this formula. So this is very expensive. This is known as the, when you increase the number of features, so it is also known as the dimensionality of the model, right? Dimensions means the number of features, right? So if you have two features like x1 and x2, then this is a two-dimensional case, right? X1 and x2, then this is two-dimensional. When you increase the dimensionality, so it is getting much and more and more complex. So this is known as the curse of dimensionality. So selecting the features, like checking all the possible feature combinations is not possible because of this complexity, right? Because of that, there are some algorithms like forward selection and known as backward selection elimination, where you can use them to get some heuristic solutions. Heuristic means we are not searching the all possible uh, combinations, but we are searching intelligently, right? So then we have, so these two algorithms can do it heuristically. So that is what we are going to learn in this one. Like this is known as a forward selection. In forward selection, what happens is, so this is the algorithm, right? So instead of looking at all the possible features, like for example, if we have, so in the feature selection, if we have feature selection, there's no particular algorithm. If we have x1, x2, and x3, so you have to try all the combinations, right? You have to try in x1, x3, x2, x3 individual. Then you have to try x1 and x2, x2 and x3, and then x1 and x3, x1 and x3, and x1, x2, and x3 all together, right? So there are different. So that is how this number of combinations come into play. But when it comes to forward selection, you don't have to do it like that. So there's a certain algorithm. What we do is we start with an empty number of zero number of features. So then we add features one by one. So that means we are, for example, if we have this x1 and x2, x3, first we check with adding only x1. And what is the performance measure that you have got? Performance measure means, so generally what we can take the increase in performance increase in test set. That means error reduction in with test set. You can use the test error as the performance measure, right? And you can test for first with x1, and then you remove, then we check x2, what is the error? Then you check x3. So if you find that the best performance is given on by x2, right? So then what you do is you keep the x2, and then you have left with x1 and x3. So you add x1 first, like x2 and x1, then x2 and x3, the second iteration. So if suppose that this one is better, right, than this one, then we select this one, and then we have only left it. Now x2 and x1 are taken. Now there's only x3. Now we try with x2, x1, and x3. Suppose now after adding x3, the performance has reduced than it was in this case. So now what will you do? You will reject this combination, and you take this these set of features as the final features that you are going to use, right? Means first we start with one number of features and select the best one, and we take the best one and then we check with two number of features, two features, whether this would give a better performance than this one. Only if only if the x2 and x1 are giving better results than x2, we move into this solution as the best solution. And then if this one is better, so then we add the third variable and see whether it is better. If it is not better than this one, so we take this one as the final set of features. This is known as the forward selection, right? So how you stop this algorithm? That means whether you, after you have taken two variables, or whether you have achieved a certain level of accuracy. So that can also be changed. So that is known as the stopping criteria. Right? So backward elimination is the other way, right? So instead of starting with 0 features, we start with all the features. So x1, x2, and x3. So what we do is, so we remove one element by one, like we try with x1 and x2, x2 and x3, x1 and an x3, right? These two, and these two. And if you see whether any of these two features, any of these three combinations are much more accurate than this one, right? If that is the case, we move to that particular solution, that particular x variable. Suppose that the x1 and x2 are better. So then, sorry, x1 and x2 are better. So then we move into this particular solution by rejecting the earlier one, and then we reduce another variable, right? We remove the x1 and look at the accuracy of x2. Then we remove the x2 and we check the accuracy of x1. And if none of them are much more accurate than this one, we stop here. So that the stopping criteria is the same, right? So you can add any stopping criteria, and you can have any performance evaluation matrix. Generally, you can use the test set error, or if your data set is small, you can use the cross validation error, right? Cross validation is a bit expensive, right? We will actually discuss cross validation later. And for both of these algorithms, like what we have discussed earlier, like forward selection and backward elimination, what is common is that those are faster than the feature selection, which is taking a lot of time, right? So these forward selection and backward eliminations are very fast, and each iteration we remove the and you can customize the stopping criteria, right? And you can use the as I said, maximum number of, for example, when you are doing forward selection, you can have a maximum number of features, right? If you are having too many features, that means suppose you have 1,000 number of features, candidate features, but you are not going to use 1,000 number of features for your actual model, right? So because practically you can't deal with 1,000 features, you may have to stop with around 30 features or something. So when the number of 30 is reached, so you have to stop. So that, or when you are removing the number of features, they are also we don't go too much to lower number, because that may we think that all the features are affecting the model. In that case, we can use the minimum number of features when you are doing the backward elimination, right? And you can use the cross validation error instead of taking the test set error. And these are heuristic algorithms. So because these are heuristic algorithms, but the performance is fast, better, like not performance, the time it takes to find the algorithm is faster, right? But the downside is that because we are following a certain algorithms, we may find some better feature combinations, right? That means suppose that you start from x1 and x2, right? So you may, when it comes to forward selection, if the x3, if you take x3 and something, it may have a better So I'm not going to give an example, otherwise you will confuse it, right? So you get the point, right? So because this is heuristic, that means because these are following a certain algorithms, there may be certain cases that are not catching into this algorithm. That means there can be some better number of features, better features uh, in this candidate feature set, which are not identified by this algorithm. So that is a possible downside of this algorithm. But because of the practicality, we use this kind of backward elimination and forward selection algorithms. And now let's discuss about feature transformation. Right? Suppose we have actually discussed this earlier in our linear regression class, right? So, for example, if you find when you draw a scatter plot between x variable and the y variable, if you find something like this, that means it is not a linear case. It is having some non-linear relationship, which may be related to a y equals x1 square, right? So if you can do a transformation by replacing x1 with x1 square, then you can get a straight line. So this is a straight line, right? Okay. You can draw a straight line. You can have a linear relationship with the y variable. So you can do these kind of transformations to match the nonlinear information into linear information, nonlinear relationships into linear relationships. Right? So those are one of the advantages of feature transformations. Right? And when it comes to certain machine learning algorithms, I think we haven't discussed much. Right? So in the future, when it comes to deep learning, especially, right? So you will have some actually there are many machine learning requirements that which are expecting normal distributions as their data sets, right? So that means the x variable should be having a normal distribution frequencies, but practically you may see this kind of left skewed distributions or right skewed distributions, and you can do some transformations to move these kind of distributions into normal distributions. For example, if the distribution is left skewed, right, you can use the higher degree power of n. So like if it's x1, you can use x1 square, or you can use the exponential of x1. That means e to the power x1, something like this. So we should move this distribution into a normal distribution. So if it is a right skewed distribution, you can use a lesser power, or that means nth root. Nth root means you can take the so actually this is not in square, it should be something like this, right? So not x1 square, so it's a mistake, right? So you can use something like x1 square root or something like this, which should move the right skewed distribution into a normal distribution. Or you can use log function, right? So the inverse of the inverse function of exponential is log, right? So the higher power, the opposite of higher power is you can use a root, right? When you apply these kind of operations, you can get this kind of normal distributions for skewed frequency distributions. So when you do the exploratory data analytics, if you see this kind of distribution, you can apply this kind of transformation and get a normal distribution before you start the process. What is it? Some better feature combinations which may return is that we will use feature combinations like better feature combinations which that we will It's like in principal component analysis. What does it mean? Some better feature combinations, better performance. Yes, that we will miss feature combinations like in you will miss feature combinations like in principal. Actually, principal component is analysis is also a way of finding better number of features, right? Better features, but in the principal component analysis, what we do is we remove the number of features, because when we find that the number of features are too much, you select some of the features that are having higher variance around it. Right? So you take the top few features uh, that are having a higher that can be that are having a higher variance around each of these features. That means because the first principal component has the highest variance, highly most varying feature, and then we take the second principal component as the next the feature that is having next amount of variance, and so on. So what we are doing is kind of data compression, right? So when we are doing principal component analysis, the idea is that when you have too much features, we want to reduce the number of features, right? So that is also a part of feature engineering, but we are not going to discuss principal component analysis in this lesson, because maybe we will have it in another lesson or something, right? So finding better features means something like this. Say that we are going to evaluate a real estate, right? So the price of a real estate, a land, right? So you have the features of as for one example I have used. So this is the land, right? So you have the length of this land and the width of this land, right? As the features. So now there are two features. So either the feature may not be related to the price, because the length or width are not related, right? So but if you take the multiplication of length and width, which is the area, right? L times W. This should be a significant, this should be a very intuitive variable, right? So this should carry the information that is highly correlated with the price of this land. That is what we mean, right? So reducing the number of features, okay. Said because there are heuristic algorithms, what kind of feature combinations do we miss? Is it explainable? Because these are heuristic algorithms. What kind of feature combinations? Okay. So that is what you're asking, right? Okay. So this is about for example, suppose in the let me go into the forward selection, right? So suppose that we start from here, right? So we start from x1 and x2 and x3, right? Suppose that you would have, suppose there are four features, x1, x2, x3, and x4, right? Just take it like this, right? So now what happens is, now we start with x1, x2, x3, and x4 individually. Right? Then what we do is, so then we move into 2. So we select that x2 is better, right? So we select x2, then we move into x2, x1, x2, x3, x2, x4, and so on. But when it comes to suppose that you are having something like x1 and x3 are the best, actually the best couple of combination of features that would be working best for our problem, right? So because we have removed this combination, like because when we are selecting this one, So we have found that we have missed X1 and X3 combination, right? So because neither X1 nor X3 are better as individual features, but X3 is performing better when it is an individual feature. So then because of that, X2 got selected. So now the model we are going to evaluate is the features that are combined with X2, right? So we start with X2 and then we try to add other features. But this X1 and X3 may be the best couple of features, right? But we haven't get the opportunity to have this combination, right? Like because we have selected X3, X2, because X2 is performing better when it is performing individually, right? So this is something like this. So you have 4 members in your team, right? So when you are having different combinations of your team, they have certain performances, right, of outcome. So X2 is a guy who is working very well when he is working alone. But there are 2 people like X1 and X2, X1 and X3, who have very complementary capabilities. Because of that, when they are combined, because of the synergetic effect, right, they will perform better. But because of this, the nature of this algorithm, it has selected X2 first, and we are going to check all the combinations that are coming with X2 only, right? So because of that, we will miss this particular this specific combination as the best combination, right? You get the point. So all the combinations that are coming after this point will be having X2 in it. But the actual in the real world, with according to the nature, the best performing team is the combination of X1 and X3. But this algorithm can't capture that capability. But if you do the feature selection, because you select all the combinations, you can select. You will find it X1 and X3. But the problem is that this is very expensive when you are taking all the combinations, right? But in this case, because we have assumed that when you find a better individual, so when you combine that individual person with the other people, only we will get better results. So that is the assumption of this forward selection algorithm, right? But in reality, there can be situations where X1 and X3 having some complementary skills, and when they are combined, so they can work with in a very high performance. But this has to be this is not identified with this forward selection. That is what I mean by this. Because of this is heuristical algorithm, we may miss some better feature combinations. I think I answered your questions. If you have any questions, you can ask. Okay. Okay. So where did we stop? So we said that. Okay. Yeah. When you are do the transformation, that is how you do it. So you can do some transformations to the x variables, and you can get a different distribution. Right? So it's not only for normal distributions, you can do for other distribution as well. Right? And there is a, and when it comes to features, feature engineering, another part is feature encoding. Feature encoding means for a machine learning algorithm to understand for a particular feature, if it is a categorical feature, it's difficult for a machine learning algorithm to understand, right? Actually, when it comes to natural language processing, you have certain ways, but when it comes to general machine learning stuff that we learn in this lesson, so they can't identify categories. Because of that, we have to convert these categorical variables into numerical values, either continuous or discrete, right? So that is why we need encoding. So how to encode the categorical variable into a numerical variable, right? So suppose that when you have a nominal variable like color and gender, so actually there are different ways of encoding, right? So because they are too complex and they are subject to the problem that we are handling, I haven't specified any of them. So I have only selected one for each of the type of variables. For a nominal variables, we can use one-hot encoding, right? For ordinal variables, we can use label encoding. So that means when you want to convert a nominal variable like color or gender into a numerical value, we can use one-hot encoding. If you have a t-shirt size, age group, or that kind of ordinal variable, and you want to convert it to a numerical variable, you can use label encoding, right? So let's see what I mean. So I will explain with an example, right? Otherwise, you will not should not be intuitive, right? So this I have taken from this YouTube video, right? For this example, suppose this is your data set, right? So now check this one. This is the outlet size. So this is about some item in some certain sales outlet, right? So don't think about that much. So like there are some dairy, soft drinks, meat, some products, and there are some outlet sizes, right? Medium, high. There are some empty values and some small values, right? So now this is a categorical variable, right? So categories means there are only three categories: medium, high, and small, right? So for these categories, in order to identify these categories, what we do is we introduce three categorical, three new features into our model, right? Like size medium, size small, and size high for each of the categories of this feature. When you have a medium sized item, you have one for size medium and 0 for other sizes. When it is a high, the outlet size is high. That means it will have high value. This size high has one value, and the other values will be 0, right? Similarly, when you convert this categorical value into this one-hot encoding, right? So this is known as one-hot. What do you mean by one-hot? That means if you take this kind of vector, right? So there's only one hot. There's only one hot spot in this vector, right? So if you take this vector, there's only one hot spot in this vector. Others are zeros. So that is why we call it as one hot encoding. So what we do is, so we transform this categorical feature, the nominal feature, into a categorical, into this, we encode this one categorical feature using one hot encoding by adding three new features which can have binary values, right? Each of the variable can have either ones or zeros. So we will put one for the category that belongs to that particular category, right? So if it is a medium size, we put one for medium and 0 for all other categories. So that is the nature of a one hot encoding, right? The idea about these nominal variables is that they don't have any order. Because of that, actually in this case we have a order, right? So small, medium, and so on. But suppose that this is a for this example they have taken this as a, actually we can use this one hot encoding for ordinal values as well, but we can for the ordinal values actually we can use one hot encoding as well, but the special uh, encoding value that can be used with ordinal values is label encoding, right? Instead, in this case, in the one hot encoding we have three features and we have only one dimension is 1 and the other dimensions are 0. But in label encoding we just state the number of this label. For example, high we take 3, small we take number 1, right? If it is small we take number 2, I think. So you get the idea, right? So medium is, so we take like for something like this, small for number 1, medium for number 2, and large for or high for number 3, right? So we map each of the categories to each of the labels, right? So we have some integer labels. We map each of the uh, uh, ordinal value, right? So these, when they are ordinal values, we can map into some integer labels. And instead of using this categorical variable, we introduce a new integer variable, right? And then we add these labels into this field instead of this category, right? So actually in this case, we have used the same ordinal variable, right? So for one hot encoding and label encoding, but one hot encoding can be used for nominal variables as well. But when it comes to label encodings, it is not recommended to use nominal variables for label encoding, because when you are having some particular label, that means has a particular number, right? So the number should have an order in it. If you represent a nominal variable like color or something with the label, so that has no meaning in it. So because of that, there may be some issues when you are doing the machine learning. But when it comes to an ordinal variable, you can either use one hot encoding or you can use a label encoding, right? You get the point, right? Okay, so that is about feature encoding. Now let's move into feature scaling, right? Actually, in the gradient descent, we have, when we were learning gradient descent, I haven't mentioned about this scaling requirement, right? But I will, because I have moved this into this lesson. In the scaling, what does it mean by scaling is that features can have different ranges, right? For example, if you take the number of bedrooms, so suppose that we are going to again we are going to predict the price of a house using some of the features of this house, right? So one of the features of a house is the number of bedrooms, right? The number of bedrooms are generally in between 1 to 5, right? And there's another feature of this house, which is the number of square feet of this house. That can be between 500 to 4,000. Right? Now, those two features are to be used in the same machine learning model, but now you see there is some scaling difference between these two features, right? For example, if x1 is the number of bedrooms, x1 ranges from 1 to 5. If the square feet number of square feet in the house is x2, it ranges from 500 to 4,000. So suppose that you are using a linear regression model, actually, yeah, a linear regression model to predict the price of a house, then your coefficients would be highly different. Like you will have a very high coefficient for the for this particular variable for x1, and you have a very lower coefficient for x2, right? Because of the scale difference. And sometimes the scaling is it's not a big problem, but when it comes to gradient descent, where we find the vector distance, right? So you have a certain vector here, you have a certain vector here. Suppose your algorithm is measuring the distance between these two vectors. In this case, when a certain dimension is defined in a certain with certain feature, and another dimension is insert another feature, if these features are having very large difference in their scales, what happens is there would be some problems when it comes to measuring these to evaluating these distances, right? For example, if you are having a very large value for in this example, if you this is the x2 and if this is x1, coefficients of so when you are having small x1 means, so you when you move here and to here, you will find a small difference, like small changes in bedrooms. But if you move from here to here, you will find a huge difference from 1,000 to 2,000 or something like this when you are moving from here to here, right? So because of that, the finding the distance between vectors would have some bias, right? So when you are doing algorithms like gradient descent, actually it would move converge, but the convergent time will get affected when you are using features with very different, highly different scales. So there's another problem with this scale difference, right? So if you can remember, we have discussed about regularization in the regularization lesson. When we add the L1 and L2 regularization components, can you remember? So what did we do? So we add some component to the loss function, right? So for the loss function, we add some particular value. So for L1, we add the value which is proportional to beta. For L2, we add the proportional to the value of beta square, right? So, but if so when you are adding these terms, we add this to all. So we assume that these x1 and these features are having a similar scale. But if you are having in this case, if you are having a smaller features, so the smallest features will have a smaller loss, but you will have a very high penalty added into it. So you will face a lot of regularization for smaller features. But for larger features, the same amount of regularization components would there are some other components, right? Like lambda or two, something like this, right? So when you add this this regularization term, you will find that you will apply the same amount of regularization for a very large loss as well, right? Suppose this loss is kind of 3 or something, we are adding a regularization component of 4. So if suppose this the loss is 100, still you are applying a regularization value like 5 or something, right? That means there's no significant difference between these two variables, right? Because we are applying the same regularization component for the loss function irrespective of the scale. So the idea is that before we apply if we are hoping to apply the regularization, we first make sure that the features are scaled into a same level, right? That means we should make sure that the x1 and x2 are scaled before we apply the regularization to expect the regularization to work properly, right? So that is another requirement for future scaling. And when we are interpreting the final results, like once you have, for example, when you have created the linear regression model, you have to interpret the values like beta 0, beta 1, beta 2, and so on, right? So if you find a very large value for beta 1 and a very smaller value for beta 2, so that may sound like the beta 1 is very highly significant, right? But that may because the beta 1 is multiplied by a very smaller x value, right? Which is having something like a very smaller feature, which is deviating from 1 to 5. This beta 2 may have very small beta value because it is multiplied with a very large feature. Because of that, we can't interpret what are the important parameters in this linear regression model. Because of that, if we could have applied the scaling before applying this, before learning this machine learning model, then we can interpret these beta 1 and beta 2. We can compare these two based on their relative importance. That is another reason why we should use scaling, right? So scaling, actually, there are two ways of scaling, right? For basically, when it comes to scaling, means we are moving. So when we have different ranges for different features, what we try to do is we want to move all those ranges into a single range, right? For example, 0 to 1 range, right? So for example, if you have the height of a person is maybe changed from 4 feet to 4 feet to 6 feet or something, and the weight from like 40 kilograms to 120 kilograms, we want to make sure all of them are lying between 0 and 1, right? So the 1 would be the highest value for any person. The 1 would be the tallest person's height, and when it comes to the weight, one would be the tallest person's weight, right? So the height and weight can be scaled in the scale from 0 to 1, so that both scales can be compared with each other. So that is the idea of scaling, right? So when you scale all those features into a single range, then you can compare these two values with each other, and you can do some predictions and interpretations, right? So there are two ways of doing feature scaling. The one is known as the normalization, the other one is known as the standardization. So let's see what is normalization. The normalization is we are trying to bring the feature in between 0 and 1 into a value in between 0 and 1. So this is the formula, right? So first what we do is, so when we have a feature, we take the minimum value of this feature, right? Which is known as minimum x. And we can take the maximum value of the x as well, which is known as the max x. So in order to scale this normalization, what we do is we reduce maximum x value from the minimum x value. So that is the range, right? So this is the range of this feature, right? Max minus min, and that is used to divide the difference between this particular x value minus minimum x value, right? So it is like this. So you have a data distribution something like this. So this is the x value that we want to predict, right? So this is the minimum x. This is the maximum x. So this is the difference between maximum and minimum, or the denominator value, right? So this is the x1 minus x min is the difference between minimum and the x value that we want to predict, that we want to scale, right? What we do is, so we divide this value by this value. That is what we do in normalization. In this case, because always the max minus min is greater than this x I minus x min, right? So whatever the value x value minus minimum value is always positive, and it is always lesser than the maximum minus minimum value, right? Because of that, this value is always in between 0 and, actually I haven't mentioned it here, right? It's always between 0 and 1. Right? So we said it in letters, right? In English. So that is the idea of normalization. So in Python, you can use a min-max scaler to do this normalization. Right. So this is the theory of normalization. So this is a way of scaling a feature. So the second way of scaling is known as standardization. I think you guys know about normal distributions, right? So standardization is also standardizing the x variables, standardizing the features, right? So the best example is our university entrance, right? So when you, for example, if you select I don't know about the commerce subjects, suppose. So if it is math subjects like combined maths, chemistry, and physics, right? So the difficulty level of each of the three subjects can be different, right? So they may have different ranges and different values. Because of that, we can't compare each of them. So what we do is we want to scale the marks of value of all these three subjects. So what we do is we calculate the Z score, right? So that is exactly what we do here. So it is known as the standardization. So what we do is, so we so because when we want to calculate the Z score, we do the same. That means once we do calculate the Z score, then we can compare the marks of chemistry with the marks of maths and the marks of physics. And also that can also be used for another subject as well, right? So for example, it's accountancy or whatever, business studies or whatever the subjects, the marks can also be compared, assuming that the students doing all those subjects are having equal amount of capability. So that means the students are randomly distributed across all these subjects, right? So with that assumption, you can use the Z-score to compare the competency levels of students. So that is exactly what we do in standardization. So what we do is first we calculate the X bar, which is the mean value or the average value of the feature, and then we calculate the variance, the standard deviation, which is the square root of variance, right? So in order to calculate the standardized value, what we do is we reduce the mean value from this particular X value and divide by the standard deviation. So then it would follow a standard normal distribution. So just forget it. Something like so the average is 0, and so actually not the average is 0. So yeah, the average is because we have reduced the reduced from the average or the mean value in this standard normal distribution. So that means after applying the standardization scaling, what we get is a standard normal distribution where the this mean value is 0 and the standard deviation equals to 1, right? That is what we get from this transformation. Once we have converted any feature into this standard normal distribution, you can compare each of them without thinking about its scale, because they are scaled similarly. So that is the idea of standardization. So in machine learning, you can use the standard scaler. In the Python language, you can use standard scaler in the standardization. Okay, right. Now is the time. Okay, 10:50. Yes. Now the other part is handling missing data values in features. When it comes to handling missing data values, so let's say so that when you find the practical data set, right? So practical data set means so you go to a company and you find that you are asked to analyze the data. Then you get the data sets. You get it as from the databases, you get it from the Excel sheets, you get it from CSV files, and so on. And then you find that some of the entries are empty, or some of the entries are as errors, like some data fields, right? So suppose the person who has to enter the value has not entered it, or that particular person who's responsible of it has gone leave on that particular day or something like that, or the value he has entered is erroneous, or it's an outlier, right? So instead of entering 10, he has entered 100. So you find clearly it is an outlier, so you have to remove it. And in this case, you will get a hole in your data set. So that means this data is not, you can't find it continuously. Some of the data are missing. You have to do something with the missing values these missing values before you start data processing, because when you are having empty values, you will have a lot of problems. Either you have to replace these values with null values. So if it is a categorical value, maybe you can use some null value or default value, or you can use if it is an integer value, you can use 0 or -1 or something. But then that would change the distribution of your data set, right? For example, if you are having heights of people and some of the heights are empty, if you put the height as 0, then when you calculate the average height of the distribution, then the average height would be lesser because you have replaced the empty values with 0 values. That is not a good practice, to replace the height with the 0 value. So what you have to do is you should remove. So there are two things you can do, right? Either you have to remove the entire row where the data is missing, right? Because the data is not complete. So suppose you have 100,000 records and several 2-3 records has some missing values. Maybe you can remove those missing values. It's not a big problem. And if the data doesn't have to be this be continually available, continually means these rows are not necessary for your machine learning process, you can remove those rows, right? Or if you find that there are some columns, data columns, that are having a lot of error values or empty values, then you may decide that this feature column or feature is not significant, or it doesn't contain enough valuable information because most of the information are empty. Then you can remove the entire column or the entire feature, right? That is how you can remove the uh, entries from your data set. Either you can remove it as a row or the data record, or you can remove the column or the feature completely. So either way, what you are doing is you are removing the value. So when you remove the value, you will lose some other useful information as well. So that is the downside of removing. So the other way, so instead of removing it, you fill that empty value with some new value, right? So some synthesized number. So what you do is you have to approximately guess the value that should have been there and add the value for that particular data field, right? So how to approximate the value that should have been there in this particular data field? So one way is, the simplest way is that actually this missing values is known as imputation, right? So when doing imputation, make sure that what you have to remember is that filling missing value does not introduce any new information into your model, right? Actually, it may destroy some of the patterns in your data set, but we are doing this imputation assuming that it would improve the pattern. So suppose that if the data is not there, or you replace it with 0 values, then you would have a lot of errors in your, like holes in your data set, right? So instead of having these kind of edges or holes in your data set, what you can do is you can add an average or something like that, or the previous value, so that the data is not having some smoother curves when you are connected each of them, right? That is the idea of filling the data, but not to have better information, right? You will not get any new information because you are assuming the value what should have there with your knowledge and the data that are already there in the data set. Right? Unless the agent that is filling this missing value is an intelligent system, like it has some other information to forecast the missing values and fill it. Unless it is the filling agent is an intelligent one, the normal ways that we are using to fill the missing values does not introduce any new information. So make sure if you have too much missing values in a certain row or a column, you can, its best thing is to remove that row or the column entirely instead of trying to filling, because filling missing values may add some new bias into your data set, right? So if you have to fill too much missing values, you have added some lot of noise into your data set, which may be deviating from its original data patterns. So that would introduce a bias. Because of that, it's better to remove them if you think it is too much. So there are several imputation techniques or the filling techniques. One is known as this median or mode imputation. Right? So that means, as I said in this example of filling the missing values of a person with heights, right? So if you have a set of heights of a set of people, in order to fill a missing value, what you can do is you can get the central tendency measure. So in statistics, I think you have learned about central tendency. Right? Central tendency is nothing big, right? Central tendency is how you represent the central value of a distribution, right? So the central value of a distribution can either be represented by mean value, median value, or the mode, right? So in a parametric distribution or a normal distribution, the central tendency is generally measured by mean. And if in non-parametric cases, maybe median or mode can be used, right? So so you can calculate that kind of central tendency, and you can you can add this central tendency value, like you can find the mean value of the feature and fill the missing values with mean value. So that is one way of imputation. And there are some other much easier ways, like forward and backward fill, the forward fill. So that can be used only if the data rows are having a order, right? So for example, if the data fields are ordered in the time series way, like in subset, they are ordered according to the time. So if, for example, if you find if you have the measurements of rainfall throughout the year, some of the days they couldn't collect the rainfall of these particular days. So what you can do is you can fill the missing values from the previous days rainfall, right? Or you can use the next days. So that is known as the filling from the previous value is known as the forward fill, right? So, and you can fill the missing value from the next value, then the next day's rainfall, that is known as the backward fill, right? So either one of them can be used, or you can use both of the values, or some other values throughout that particular month and get an average value or something, or you can draw a particular interpolation curve, or you can find can apply it to an interpolation formula and get a certain value and add it into your missing value. So that is also a imputation technique. And also you can use some much more advanced way of filling missing values, like you can do the linear regression for the data set, and you can predict what is the value that should be added into a set added in as the missing value, or you can use we haven't discussed this yet, like k nearest neighbor algorithm for clustered data. You can find not a class, yeah, how these nearby data points can be used to estimate the value for that particular unknown data points. Right, so these kind of machine learning techniques can also be used, but make sure that remember that none of advanced techniques can introduce more information into your model. So what it does is it would use the existing information in your data set and try to estimate the value for your missing value, right? And suppose that introducing some central tendency, for example, too much into your data set, what would happen? Right? Just think about it, right? Suppose that you have a set of heights, like a data set, a feature of heights of people, right? So once you have replaced these missing values with the mean of these heights, what would happen to your distribution? Yes, your mean value of your heights will stay the same, right? So once you replace the missing values with mean height of a person, then the mean height of this distribution will get unchanged because you replaced with the mean value. But what happens to the variance or the standard deviation? Or in general, if you talk about about the dispersion of the distribution, because you have replaced the empty values with the central tendency, then the variance will get reduced, right? The variance will get reduced because you have we have too much central values in our data set. So that is a problem, right? In some of the cases, right? So in that kind of cases, what you can do is you can estimate the probability of having a particular height. Instead of taking the mean value, what you can do is you can assume, for example, if you think that the height of person follows a normal distribution, right? So I am writing with my unfamiliar hand, so forgive me, right, for my drawings. Okay, so suppose that this is your actually this cannot be, heights cannot be negative, right? So sorry, you get the point, right? So you have a normal distribution of heights. So this is not correct, right? And what you can do is once you know the mean and standard deviation, what you can do is you can generate some new values for the height, right? So that means you can randomly generate certain values for the height using this as a probability distribution, right? So when you use this kind of probability distribution and generate values out of it, it may have different values with the probabilities of having a mean of the distribution, and with the same and with the variance of the distribution as well. So in this case, the variance would because we take samples from this distribution, probability distribution, the variance will also not get changed if you if you can do this kind of sampling technique for filling the missing values, right? Okay. The other feature engineering thing is feature generation, right? So as we discussed earlier, feature generation is also it's very important when it comes to extracting information from the data, right? So the data so with feature generation, you actually don't generate new information, but what you do is you there are some hidden data hidden inside your data sets, right? So in some features, your data is hidden in these features that cannot be consumed directly by your model. So what you do with feature generation is that you extract those information and create new features. So with these new features, your machine learning model can learn new stuff or do it much more accurately because this new information get exposed into your new machine learning model. Right. So that is the idea of feature generation. In order to extract the information from your existing data set or the existing set of features, you should have a domain knowledge about this problem. Right? For example, if you are extracting data to predict a particular disease of a patient, you should have some knowledge about medicine, how to extract the relevant information and create this new feature out of the data set. Right? So that is what we say is we do need the domain knowledge to generate features. And so there are several feature generation techniques like polynomial features. We have discussed it earlier, right? So instead of using the feature directly, you can take the polynomials of the feature. So not only higher degree polynomials, also the lower degree polynomials as well, right? Like square root of x. And you can take the interaction features. That means you can combine several features to create a new feature, like multiply the length and width of a land to model the land price, which we have discussed many times, right? And there's another way of feature generation known as binning. So binning is nothing new, right? So if you have, for example, ages of a population, instead of having, so these ages are a continuous variable if you take it as the time step, right? So instead of having it as a continuous variable, you can group it into several age groups, like lesser than 5, from 5 to 10, 10 to 30, and so on. So like converting, so like taking these numbers and put it into a bin or category is known as the binning, right? So when you do the binning, it would help to reduce the overfitting because this extra information that was there in this or the noise that were there in this particular class will get eliminated once you remove all this continuous information and represent them with only a single class number, right? Instead of having a complex, instead of having a continuous value, which can have infinite number of values. Once you replace it with the categorical variable, you lose a lot of information, mostly the noise information. So that can reduce the overfitting. Right? Okay, so that's all for today's lesson actually. If you have any questions, you can ask. Or you can start today's tutorial. I don't know whether it is added yet. It is added, we can start it. So I will stop share. Let me check. Okay. Actually, wait a minute. I think I have added so there's a tutorial kind of thing link that is given, and also there is a video that I have added, right, about feature engineering, which is around 1 hour, right? So I think we don't have that much time to watch it now. Mm, but we can double the speed and see, right? So which contains all the information in it. Let me share the screen. So there's a kind of tutorial that is given. Let me share my screen again. Can you guys see the screen? Can someone answer, please? Or either you can watch it at home, right? So because there's not that much time. Or just look at it so you can get some good understanding, right? So shall I play it or what? Okay. For what? For you have answered yes for what question? Sorry. We will watch. Okay. 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 No need to then. Okay. Okay. Okay, then you guys can do it yourself. Okay. If you guys have any questions, you can ask, right? I know you guys are not asking any questions. Why is that? Uh, Actually, if you guys have any questions, not in this lesson or up to this lesson, you can ask, right? Even in previous lessons, that is okay. For this feature engineering, you have to practice it, right? So it is more about practicing. It's not like a simple code that you have to remember, that you have to do the stuff with Python. That is what makes you capable of feature engineering. You have to do a lot of tasks by yourself, and then only you will get familiar with feature engineering. If you have any questions up to now, you can ask. Like the one is someone has asked me about this what is the heuristic in this forward selection algorithm. So that is a good one, right? So I think that is not necessary, but then only I got to know that this is important to explain. So if you guys have these kind of questions, definitely you can ask. There's nothing as good questions or uh, stupid questions. Right? So whatever the questions you have, you ask. Because if you know everything, you don't have to ask questions, and you don't have to come to lectures. Yes, if you ask me because you haven't understood, maybe I haven't explained it clearly or something. That is okay. Just ask. If you can't directly ask, you can ask via your batch rep, or you can simply directly send me a email or meet me or whatever. I don't know what you guys are doing, right? No, no sound. So I don't know whether you are sleeping or what are you doing? If you have any questions, so there's a tutorial, right? Even online tutorial. Maybe you can go through it. Okay. Yeah, yes. We'll do. Okay, okay. Actually, it's better if you can watch that video, right? So because so that would be actually far better than what I have explained. So it explains with some code examples and so on. Within 1 hour, it explains almost everything very clearly with all the examples written in Python notebook. So don't miss watching it, right? So just watch it and do it yourself. Try to code it yourself, and then you will get a good understanding. Okay, because I am staying here without any work, you guys can ask any unclear sections in the past few weeks, right? So that is okay, right? So then we others can also clarify it. If I am not clarify, I can clarify it by myself, for myself, and then let you know. That is okay, right? If you have any, you will have, right? So some of the sections that are unclear, if in that case, just ask me.
සර් ඊළඟ ක්විස් එකට මොන ටොපික්ස් වලින්ද එන්නේ?
ඒකට ඊළඟ ක්විස් එකට ඒ වෙනකන් කරපු ටිකෙන් තමයි දෙන්න ඉන්නේ. මෙහෙමනේ අන්තිම සතියේනේ ඔක හදන්නේ. එතකොට ඒ සතිය වෙනකන් කරලා තිබිච්ච ටිකෙන් තමයි දෙන්නේ. මේ ඒ කියන්නේ අන්තිම so we will start from where we have did our last in class quiz, right? එදායින් පස්සේ කරපු ටිකට මේ ඒවයින් තමයි දෙන්නේ. ඉඳලා අන්තිම සතිය වෙනකන්. ඒ කියන්නේ මෙහෙමයි දැන් ඔයගොල්ලෝ මම අහුවනේ මොනවද ඉස්සරහට උගන්වන්න ඕන කියලා ඔයගොල්ලෝ එහෙම කිව්වොත් එහෙම ඒවා අපිට ඇඩ් කරලා බලලා එතකොට ඒ අනුව ඉස්සරහට අරන් යන්න පුළුවන්. ඒවා ටික අරන් ගිහිල්ලා ඒවයින් තමයි මම මේ MCQ questions හදන්නේ. ඉතින් බලමුනේ. Next week maybe we will be doing decision trees and ensemble models, right? So that is the expectation. We will see, because sometimes we miss our classes ne. මිස් වුණත් අපිට lessons ගන්න අඩු වෙනවනේ. ඔයගොල්ලන්ට ඇත්තට මොනවද අමාරු කියන්නේ මේ තියරි තේරෙන්නේ නැති එකද නැත්නම් ප්‍රෝග්‍රෑමින් අමාරු එකද මොකද ඒ විදිහට කියන්න ටිකක් නිකන් අන්මියුට් කරලා කියන්න බලන්න කවුරු හරි මොකද්ද ඔයගොල්ලන්ට අමාරු කියලා හිතෙන්නේ මොකද්ද? That's okay, because there's a nice story about me, right? So I was learning artificial neural networks in around 2009 or something in nowadays Department of CSE, right? Computer Science and Engineering. So that was a visiting lecturer who was teaching us artificial neural network. So after his at the end of his lesson, so he asked, what are the questions that you have? So no one asked, and I asked him to give a summary. So actually, he gave a summary about the because I feel no one had understood it, everything. Because if you need that kind of summary, also let me know so I can tell it. Or if you have some questions. ප්‍රසිද්ධිය අහන්න කැමති නැත්නම් මේ personally හරි දාන්න message එකක්. මේ එක අවුලක් නැහැ. මොකද ඔයගොල්ලෝ එක්කෙනෙකුට තියෙන ප්‍රශ්නයක් කියන්නේ ඒක මේ අනිත් හැමෝටම තියෙන ප්‍රශ්නයක්නේ. තේරෙනවද? ඒ කියන්නේ ඔයා හිතුවට ඔයාට විතරයි ඒක තේරෙන්නේ නැහැ කියලා මේ ඒක ඇත්තටම මේ ඔයාට විතරක් තේරෙන්නේ නැතුව නෙමෙයි තව ගොඩක් අය ඉන්නවා තේරෙන්නේ නැතුව මේ අහන්නේ නැති අය. එතකොට ඔයාගේ ප්‍රශ්නෙට උත්තර දෙනවයි කියන්නේ අනිත් තේරෙන්නේ නැති අයටත් උත්තරේ හම්බෙනවයි කියන්නේ. ඒක නිසා මේ ඒක වටිනවා ඉතින් සෑහෙන්න. එක්කෙනෙක් හරි එහෙම කියනවා කියන එක එතකොට අනිත් අයගේ උත්තර හම්බෙනවනේ. This applies for like product reviews as well, right? So when you go to a certain shop or when you buy something, when they ask feedback, so 99% people don't give feedback or something. So when 1% gives some feedback, so then the company knows that that 1% represents this 99% who are silent. So actually there may be a certain bias when you're collecting this data, right? But because only a certain type of personalities may respond to your feedbacks. But since there is no other way to collect data in a proper way, unbiased way, so the company has to depend on the data that they would have collected with the feedback. So they would take measures based on the feedback that was given. Right. So the same thing applies for these lectures as well. So actually almost no one is asking questions. So if someone asks and says someone tells something, so I think that is what you are. These things you are not clear. Those things you have to improve. These lectures are not organized well, right? Some of the things that I have told earlier that has to be mentioned later. So I may be unaware. I may have gone wrong, right? So definitely those things happens, right? So I may tell something that should be told in a later stage. So at least in the next year or something, I can correct it, right? So that is a help for me. Right? I am doing the same this lecture in the MBA in class as well. So if you guys can give a good feedback, I can correct them in the next in the MBA and lesson as well. Like it is too much, too little, too fast, too slow, too mathematical, highly theoretical, or not organized. These things should be organized in a certain other way, like the feature engineers should come earlier than the these machine learning models, or whatever the way. Just send me an email, okay? Whatever you think that hasn't to be correct, right? So don't overthink. Just send me a email. I have given my email address, personal one and the university email addresses. So you can send to either one of them. if you want. If you want, means you definitely have problems, right? So otherwise you should get 100 marks for all the exams. So that means you should have some problems. Just ask me so that in the upcoming lessons, those will be much easier, right? So the last week, or I think, is the most difficult lesson about support vector machines, right? After that, it would not be much difficult, I guess. Support vector machines, don't worry, right? So difficult means it is. So what's the difficult is you can't connect the maths that was there, right? So that is as it is, right? So I haven't given the way to connect all those theories, right? Because it is too complex. Because of that, it may feel like difficult, but don't worry, that is okay. But other lectures, other lessons, if you have any doubts or something, just tell me. I don't know whether I have given the correct. I have clearly answered this question about this principal component analysis, right? Like the difference between this feature engineering, the feature selection, and principal component analysis is that in feature selection, what we do is we are given a set of features like candidate features, and we select the best fitting features. Right? Feature engineering, what we do is we create new features that would give much accuracy to our model. Right? In the principal component analysis, what it does is it is trying to minimize the number of features by creating another set of features. Right? So it's trying to compress all those features and represent them with some other set of features. Principal component analysis, this once you have transformed into principal components, these principal components becomes new features, but these new features will have no physical meaning, right? Like they are just mathematical features, like which that means empirically defined features, but they won't have any physical sense. So we select these principal components so that the dataset can be represented by the principal components as much as possible. So the first principal component is the one that has the highest variance around it, and so on. So it is also actually a form of feature engineering, but things that we have discussed in the today's lesson is a bit different, right? So what we have learned is how to filter out the features, how to identify the best features using feature selection, like and some feature selection heuristic algorithms like forward selection and backward elimination, and how to scale the features and all those things. But principal component analysis can also be used to reduce the number of features in a data set. So if the number of features are too large, maybe you can use PCA. So there's another type of these things are known as dimensional reduction techniques, right? So principal component analysis is a dimensional reduction. So dimension is the number of features, right? So when you want to reduce the number of features, these techniques are known as dimensional reduction. So PCA is just one of them. So there are some other techniques like internal component extraction, like internal component analysis. Like, so we try to find what are the features that are hidden inside a particular data distribution. There are that kind of transformations as well. Right? So all of them are actually feature engineering, but we haven't discussed it today because those are separate lessons, right? So, ඔයගොල්ලෝ මේ නේද මේ ට්‍රිප් එක යන්නේ අඟහරුවාදට අඟහරුවාදට නේද යන්නේ ට්‍රිප් එක Okay, we will discuss it later. You guys can do it yourself, right? So shall we finish the today's lesson then? If you have any questions, you can ask. Otherwise, we can finish it, right? So this is getting a recording. Is that okay? Shall we finish the today's lesson? Are you guys okay, or do we need to do anything? We have 5 minutes more, but okay. Thank you, Sanjula. Okay. Sanjula, sorry. Okay, shall we wrap up the meeting? So this recording will go to our Dr. Tiloka's cloud, I guess. So maybe she will send the link, I guess. Okay, then. And see you again. Bye.